We are starting with just kind of describing some basic functions we already know, and then talking about a couple new ones. We are beginning with the function f of x equals x. What kind of graph is that? It is a line. It is positive. That is true, but it is a line. What's the domain of that function? All real numbers, negative infinity to positive infinity. However you want to write that, they mean the same thing. So domain is all real numbers. What about my range? Okay. So that just means that forever and ever my graph is extending out left and right, as well as my graph is extending top to bottom. We are on page 331, by the way. Okay. So then we talked about on Thursday or Friday, I think it was Thursday, we talked about the idea of end behavior. And we discussed that end behavior literally means what is the graph doing at the very end. So when it asks for as x approaches positive infinity, so if x is approaching positive infinity, which end of the graph am I looking at? The right end. So I'm going to write that up here, that it is the right end of the graph. So if I look at this function, the linear function, the linear parent function to be specific, the right end of this graph is going where? Up, so it's going to what? Positive or negative infinity? Positive. So we just write positive to specify that it is not negative. Okay, what about the as x approaches negative infinity? That's talking about which end of the graph? The left end of the graph. So over here, which way is that side going? To, yes, to negative infinity. So that would be my end behaviors. Right. So the next function, f of x equals x squared, what function is that? A parabola. Okay. What's the domain of a parabola? All real numbers, because it continues to expand further and further and further left and right. That never stops. Okay, what about my range? To the top in this case. Where's the vertex of the parent function? 0. Yes, so it's y is greater than or equal to 0. So then when we compare our end behaviors, okay, so x approaches positive infinity. That's the right end of the graph. Where is the right end of the graph going? Up to positive infinity. Okay, what about as x approaches negative infinity? Where is the left end of the graph going? Up, 0. It's also going up to positive infinity. So is it okay if they're both going up towards positive infinity? Absolutely. Yes. Why is that happening on this graph, but it didn't happen on the other one?
Because it's not a parabola.
It's a parabola. Okay.
Not a parabola.
It's not a parabola. That's not how we say that, just so you know. Okay. Not that one either. Okay, so what about the next one? F of x equals x cubed. We learned about that one on Thursday and Friday. It's a squiggle. That's a good name for it. I like that name, squiggle. Okay, so what is the domain of our squiggle? All real numbers. And what's the range of our squiggle? Okay. Where is the right end going? When it says x approaches positive infinity, where's the right end of the graph going? Positive infinity. What about as x approaches negative infinity? It's going to what? Negative infinity. Okay. All right, f of x equals x to the fourth. You should probably graph it then. All right, when you graph x to the fourth, it kind of looks like what? A parabola. It's actually a little bit narrower than x squared, because that makes sense, because when you square something versus like when you take something to the fourth power, when you take something to the fourth power, it's going to get bigger quicker. So it's just like a skinnier version of a parabola in a way. What is the domain? Because it's going to continue to get wider and wider and wider. What about our range?
Wouldn't it be? Yeah, the same as the first one.
It'd be y's that are greater than or equal to 0. It's going to be the same as x squared. Okay? So what about my end behaviors? Where's the right end going?
Up.
Up to,
Positive infinity.
and the left end is going, okay. So what speculations could you then make about x to the 5th and x to the 6th?
X is 60.
The tighter version of it.
Okay, so let's start with x to the 6th. What's that one going to look like?
It'll be a tighter version of the parabola.
Yes, it's going to be an even narrower version of the parabola. So then my domain is going to be what? All real numbers. And my range is going to be y that are greater than or equal to 0. Yes, and x to the 5th is going to be an even skinnier version of x to the 3rd, or squiggly. Our very technical term there. So my domain is going to be all real numbers. My range is also going to be all real numbers for x to the 5th. What about my end behaviors of x to the 5th? My end behaviors of x to the 5th. It's going to go from positive, as x approaches positive infinity, it's going to positive infinity. And as x approaches negative infinity, then it's going to negative infinity. What about x to the 6th?
It'll be the same as X to the 4th.
They're the same as the parabolas. They're both going to be positive infinity. Okay. Why is that?
Because that's what the math got.
That is not why. Why is that?
Wait, why is what? Like which part?
Why is it that like x to the 6th looks like x to the 4th?
I say because every time it's like x squared or something, it'll be
Because the
tighter.
odds and the evens out.
They have to do with their odds and their even exponents.
Oh, so I was right.
So if they're even exponents, they're going to open up. Both ends are going to open up. All right, what would happen if I were to make all of these functions negative? What would that do?
Parabola will open down.
Okay, so everything would change and open the opposite direction. So what all would that affect? Would my domain be affected at all?
No.
Would my range be affected?
Yes.
For all of them or just some of them? Just the even ones for the parabolas. Okay, what about my end behaviors?
It'll be a negative infinity for both.
They'd always be the opposite. Because when I open my graph the other direction, then my end behaviors end up flip-flopping. Okay. So we are going to look at these three functions on page 333. X cubed, x squared times x minus 2, and then x times x minus 2 times x plus 2. And we're going to determine some attributes about them. So for right now, for all of them, we're going to skip the first box. Don't mark it out. We're going to fill it back in a second. But for right now, we're going to skip the first box on every single one of these. And we're going to start with what are the x-intercepts. So starting with x cubed, this is the graph of x cubed. So I've already pulled it up for you. You can graph it on your calculator if you want to, but I already have it graphed here for you. What is the x-intercept of this function? 0. So it goes through the x-axis at 0. So I'm going to go and fill that in up here. That the x-intercept is at x equals 0. So the next question is kind of a weird question. It asks us, is the graph tangent to the x-axis at that point, or does it cross the x-axis at that point? So that's a good question. What does tangent mean? Not laying on it. Close, though. It barely touches it. It comes down, touches it, and goes back away. Okay? So the question is, does this graph touch the x-axis at 0, or does it cross the x-axis at 0?
Cross it.
It crosses it. So we're going to put that in our next blank, is that it crosses the x-axis at 0. Okay, the next question asks, how many turning points does the graph have? So when you think about turning points, think about it as if you're like, it's when the graph changes from increasing to decreasing. So if I were to follow this graph from the bottom, is this function always increasing, or at some point does it change?
It's always increasing.
So that means that there are no turning points here. Okay? There are 0 turning points in this function. There are 0 turning points. Now, this next question is super weird because we've got some new vocabulary. And it asks how many global maximum values, how many local maximum values. The next one, how many global minimum and how many local minimum. So think about the words global versus the word local, like totally non-related to math, just in general terms. Like when something is global, what do you think of? The whole thing, right? When you say something is local, it's like this little bitty area. It's like looking at Crandall. That's the exact same thing when we're looking at graphs. So our graph can have like the whole function can have a maximum or minimum, but then sometimes we have maximum or minimums in these little bitty areas. I'm going to tell you that this function has none of either, okay? There are no global or local max or mins. And we're going to look at one in a second that has those so that we can talk about like what that means. All right, so our next one is x squared times x minus 2. So that function is the next function that I've graphed for us. So starting off with x-intercepts. That's this red graph here in the middle. Does it have any x-intercepts? How many? Two. There's one of them at 0 and then another one at 2. Okay, so I'm going to go ahead and fill that in. That I have an x-intercept at 0 and x-intercept at 2. So I'm going to write x equals 0, x equals 2. Okay, the next question asks, are they tangent or do they cross? So talk to me about 0. Is the graph tangent at 0? Does it touch at 0 or does it cross the x-axis? It is tangent. Think about when you cross something. That means you go from one side to the other side. So if you look at this point right here, do I ever cross the x-axis? No. Do I cross the x-axis here? Okay, so at 0 it is tangent and at 2 it crosses. So I'm going to write that. Tangent at 0. And crosses at 2. So when you look at this function, when you look at a cubic function, okay, think about the fact you guys told me the word global meant like over the whole thing. So when you look at a cubic function, is there an actual like maximum value in a cubic function? No. No, because what's the domain of what's the range, I'm sorry, of our cubic functions? All real numbers. That just means it goes on forever and ever and ever. It never stops going up. It never stops going down. So there's no maximum or minimum, no global maximum or minimum. However, if I were to look at this part of the graph right here, is there a maximum in that part of the graph? Yes. That is what we call a local maximum. Because in this little bitty area, in this little bitty part of Crandall, then that point is a maximum. So there is a maximum at 0. There's a local maximum at x equals 0. Is there, in this same function, a local minimum?
Yes. Absolutely so.
Yes, my local minimum would be here. Because in this little area right here, if I were just to zoom into that part, that point is a minimum value. So on this interval, in this little bitty piece of it, locally, there is a minimum value. I'll tell you that is the fraction 4/3. So this has a local minimum at 4/3. All right, so last one, x times x minus 2 times x plus 2. So how many x-intercepts does it have?
3.
Where are they?
-2 and +2.
Okay. So I'm going to write those down that I have 3 x-intercepts at x equals -2, x equals 0, X equals negative 2, x equals 0, and x equals positive 2. So at those 3 points, the question is the graph tangent or does the graph cross? It crosses. If it was tangent, what would it look like?
It would, yeah.
Just touch it and then come right back down, or touch it and go right back up. So it crosses at all 3. Okay, I'm going to write that down. Crosses at all 3. The next question wants to know how many turning points does it have? So it goes up. What happens then? Goes down, and then it goes. So how many turning points were there? 2. Okay. Did it have any global maximums? Does it have a local maximum? Okay. So it has a local maximum. You can tell me it's like somewhere in here. Not really sure. It is like negative 1.2, I think, actually. So there's a local one at x equals negative 1.2. Is there a global or local minimum? Local. And I'm going to tell you that one happens at x equals positive 1.2. How many distinct factors does this problem have? How many distinct problems does f of x equals x times x minus 2 times x plus 2?
No one.
Distinct means like different factors. There's 3. What's one of them? Okay. What's another one? X minus 2, x plus 2. So there's 1, 2, 3 distinct factors. Okay. What about the next one? So moving to the left, x squared times x minus 2. How many factors? 2. What's my first factor? X squared. And my second distinct factor is x minus 2. Okay. And then what about f of x equals x to the third? How many distinct factors? 1. And that distinct factor is just x. The number of distinct factors determines the number of x-intercepts. That makes sense because, so one of the things that we learned a while back was that when we have something like x times x minus 2 times x plus 2 equals 0, there's this thing called the zero product property that says if I'm multiplying some things together and I get 0, then one of those things has to equal 0. So x equals 0, or x minus 2 has to equal 0, or x plus 2 has to equal 0. And if you were to solve x minus 2 equals 0, what would you get? X equals 2. And if you were to solve x plus 2 equals 0, what would you get? That's where your 3 x-intercepts come from. It's from each of those factors. X gives you 0, x minus 2 gives you positive 2, and x plus 2 gives you negative 2. Is that true every time?
No. Yes.
Is it true with these 3 examples?
Yes.
It is true all the time. Okay? So here's the next question for you. What was different? Like there was something, like what's different between these 3 functions? Okay, so it started off as cube, then it was second, and then it was to the first. Did that affect anything?
No.
Oh. So the only time in this whole table that it was tangent was when there was x squared. What's different about that factor versus all the other factors?
It's even.
It's even. That's what you need to know. If it's even, it's going to be tangent, and therefore if it's odd, it's going to cross every time. So at tangent, that happens when the exponent is even, and it crosses when the exponent is odd. So if it has 3 distinct factors, then how many x-intercepts does it have? 3. What's the first one? Okay, and that comes from x squared. Okay, what's my second distinct factor? X minus 2, which gives me an x-intercept of positive 2. That comes from x minus 2. And my third factor was x plus 2, so my x-intercept is going to be negative 2.
That was nice.
Last question. What's going to happen? Are they going to be tangent or are they going to cross at those points? What about at 0? What's going to happen?
They're gonna cross.
What's going to happen at 0?
It'll cross.
Look back at the equation. Where did the x equals 0 come from? Where did x equals 0 come from?
X squared.
X squared. What's the exponent? It's even, so it's going to be tangent. Okay, what's going to happen at x equals positive 2? It's going to cross. Why is it crossing at x equals 2? Because the exponent in there is odd. It's just x. And then when x equals negative 2, it is going to cross. Because, again, that exponent is odd.